Hi everyone, this video is going to span 8.1 to 8.3 as an introduction to solutions. This video is going to assume you have mastered your knowledge on stoichiometry, basic stoichiometry calculations, including limiting reagent and calculating moles when given mass. Before you even start this section, I highly recommend you finish your assignment. That is going to be worth marks, the problem set, so that you don't confuse information from this video with the ones we've done before. Yeah, so again, stop the video and move on if that is you. We are going to hash out some of the more background details, the logistics of solutions specifically, before we get to the nitty-gritty. I am going to quickly talk about the big picture of this entire chapter and why the heck we need to cover what we need to cover before we get to the math of it. I'm going to give you a quick summary, as short and sweet as possible, so that you know the direction that we're heading. And to do that, I need to review some of the things, some of the special things about water that you may know already, but in case you don't, I need to cover it. Please also know, if you do not wish to watch this super long video or whatever, there is these 3 pieces that I'd like you to work on your own time. There's a quick reading. Again, it's all just sort of small details that will help you cover, how shall I say, smaller piece of information and sample problems and whatnot that might help you in answering questions along our journey to learn online. Okay, so let's get started. So this chapter, what is the big picture? Up until now, we have been studying moles. Okay, we were able to calculate moles based on mass. We were able to calculate moles based on a gas volume at a specific temperature, and we were able to calculate the number of moles from the number of molecules divided by the Avogadro's number, of course. And then chapter 6, we focused on just that because mass is probably the more commonly used measurement when we do labs. It's the most practical. Okay, what is another form of, what is another way we practice chemical experiments in a lab? It's not necessarily in mass or in the form of a solid. It could also be in the form of an aqueous solution. So how do we deal with stoichiometry? How do we deal with moles and quantitative measurements when we are working with aqueous solutions? Okay, that is where we are going. Solutions, or any kind of liquid mixture, I suppose, is always going to be measured in volumes. It's very rarely ever measured in grams. And so how can we take moles and quantify it in a situation where all you have is volume? Okay, in short, so this is the long story short. Moles inside a volume of water. How do we perform stoichiometric calculations? This is the point, main point. How do we perform stoichiometric calculations for solutions when we don't have mass available? Or it's not, mass isn't given to us or whatnot. Okay, that's our main point. Before we do any kind of, math that directs us to these stoichiometric calculations for solutions, I need to review, and you need to review, certain properties of water that will help us understand where we're going, okay? Honestly, at this point in time, I'm gonna give you the option. You can stop the video, just stop watching completely, and just read through these pieces in chunks and answer these questions. And you can move on to the second video afterwards. Okay. But if you are still with me, First thing I want to do is quickly go over chapter 8.1. And what does that tell you? It talks about how water has hydrogen bonds. Ring a bell? Okay, what does that mean? Long story short, water is very, very polar. It has an incredible ability to dissolve compounds that are also polar, that is ionic. Okay, number 2, then we move on to chapter 8.2, and it discusses this thing called dissolving. Okay. Dissolving simply means that whatever you are discussing is now a solution, okay, by definition. When we have a solute that dissolves into a solvent, we have a solution. What is a solution? It is not the answer. We're not talking about math here, okay? A solution is a homogeneous mixture of one phase, where the solute is uniformly distributed, surrounded by the solvent. I'm using words and I'm basically using terms that you may have heard of, you may have seen in grade 9. Do you remember the classification of matter where we had, matter, we had I'm going to erase this in a second, but don't copy this. Matter, and it broke down into pure substances versus mixtures, and the pure became element, compound, and this became homogeneous or heterogeneous. It's basically that, okay? It is a homogeneous mixture of one phase. And one thing I can say about that for our purposes is that it's generally going to be transparent. So that is one way you can identify. If you know you mix two things, do you know if it's a homogeneous mixture? You will see that it's typically transparent. If molecules are uniformly distributed, it's going to be transparent. So what if it isn't? If it is translucent, or even opaque, it is going to be something we call a heterogeneous mixture. What would that be? A mixture of two or more phases, not uniformly distributed. And what does that mean? It is going to be either translucent or opaque even. Anytime you see light being blocked, so anything solid that's, you can't see light through, you can't see through it, or light is being, disturbed, it is being scattered, so you can't see through it clearly, grade 10 optics, it's going to be heterogeneous mixture, right? And I'm going to ask you to stop right now. You can stop the video, go ahead to your textbook, read chapter 8.2, page 376 to 380. I highly recommend you just sort of skim through it, see what it has to say about water in general, about mixtures, about how, water affects compounds in a sense, and answer questions 1, 3, and 6. Go for it. When you're ready, return to our discussion. I'm going to move on and start talking about, information, some of the content that is discussed in 8.3. At this point in time, instead of watching me erase all of this neatly, you can go down to the comment section and press the timestamp that gets you to chapter 8.3. Okay. Let's do it. Depending on how much solute is dissolved into the solvent, we can say that the solution is concentrated or dilute. Those are words you may have thrown around casually, but in chemistry, it has a very important meaning. So a dilute aqueous solution versus a concentrated aqueous solution. Okay. Visually, why not? Let's do this visually. If I have a body of water with another body of water, I could take a certain mass, or let's be more specific, a certain number of moles of a solute, and I could sprinkle it into this body of water, and obeying just the natural chaotic tendencies of the universe, it is going to spread out on average an equal distance away from each other, okay? And these particles, or just for the sake of simplicity, number of moles, there aren't that many number of moles per specific amount of volume. Now, I wrote this intentionally as a bracket because you're going to see this ratio quite often. This is how we calculate the concentration. It's like concentration in layman terms is how many moles is in this entire body. Now, this fraction versus this fraction. Let's pretend instead of 5 dots, so in this case, let's pretend it's 5 moles over the certain volume of water. Let's keep it simple. Let's pretend this is 1 liter. Okay, 5 over 1, that's going to be 5 moles for every single liter. Okay. Let me clean that up a little bit. That's going to be 5 moles for every single liter of water. Now let's pretend I sprinkled a whole bunch more. How many dots is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I have a lot of moles in the same volume of water, right? So if I have, in this case, 14 dots, 14 over 1 liter, that's going to be 14 moles per liter. So you can say, just visually, this has more dots than that. So this, the one on the right, is a more heavily dissolved, I guess, solution. It has more moles dissolved in the water. It is more concentrated. That's simply it. Okay. Just a quick note, notice how both of them, I was talking about it as an aqueous solution. Aqueous solution means that water is the solvent. It's sort of taken for granted that water is always the solvent because it's considered the universal solvent. But when we say aqueous, you know, the word aqueous, root word, aqua, okay, Greek Latin, and I think you know what I'm going with that, where I'm going with that. So water is going to be our solvent. Now, this general idea naturally brings us to the idea of, okay, well, this liter of water can dissolve 5, it can also dissolve 14. What is the maximum amount that you can dissolve in 1 liter of water? That brings us to the concept of whether something is saturated or not, okay? So this would be, I need to go to the next topic. So unsaturated versus saturated. It is the word saturated is probably the most, this word stuck with me. And it's so easy to use the word saturated in a variety of ways. For example, if you say, yo man, the club is saturated, it's not the coolest thing to say, but you get the point. There is a certain amount of space in the club, and if it's saturated, that means that it has maxed out the capacity of people, right? In the same, let's tone it down a notch. If you say the streetcar downtown in TTC, a streetcar was saturated, That's a very loosely fitting description that the streetcar cannot hold any more passengers. It means the same thing. If a solution is saturated, it basically cannot hold any more moles. Okay? In a sense, solution cannot hold or dissolve, okay, or dissociate any more moles of solute. Okay, so it's basically maxed out. How does a solution actually max out? Or how does a solution become saturated? Well, again, to understand that, you have to go back to the properties of water and understand what it means to dissolve, or what it means to dissociate. Let's put it this way. You're going to probably read a little bit more about this in chapter 8.3 when you do the readings for me, but I'll talk very quickly. When something is saturated, there is no longer enough water molecules to effectively surround any more ions in the water. Okay, please remember, when we have an ionic compound as a crystal lattice, water molecules, being polar, will start to pull and quote unquote attack the exposed ions. Now, right now, all the oxygens are sort of attracted to this particular corner because oxygen, being more, I guess, negatively polar, is attracted to the positive ion in the crystal lattice. And it'll start to pull each one by one, and every single ion is going to be happily surrounded by water molecules. And if it's a minus, it will be happily surrounded by the positive side of the water molecules. Okay? But as I said, what makes something saturated? Well, let's pretend every single cation and every single anion is successfully surrounded by water molecules. And the water molecules are moving around everywhere. They're just completely busy surrounding with whatever's in there. And then you sprinkle a little bit more inside the body of water. Now this is completely exposed, right? It's completely exposed to the water, but is there any more water molecules available to go surround it? Well, no. If this water molecule, let's get a different color just so that you can understand what I'm trying to say. If this water molecule ends up coming here, and then this water molecule ends up coming here, and this water molecule ends up coming here and starts to attack and starts to pull away the cation from the anion. That's great and all, but in turn, that will start to expose the ion that was already surrounded. So at the expense of, by surrounding the new molecule, the ionic compound, the molecule of the ionic compound, it unfortunately, as a result, ends up exposing another one. So surrounding the ionic compound on the right versus surrounding the ionic compound on the left, what's the difference? Nothing. So why bother? Okay. That's all it is. The general idea of water being able to dissolve up to the point where it maxes out or it saturates itself, if the solution is saturated, is something that I would like you to familiarize yourself with. At this point in time, I'd like you to stop the video and quickly skim through the idea presented in chapter 8.3, numbers page 382 and 383. It's about dissolving and how that dissolves. And answer question 1. There is a sample problem also in page 383, so you can take a look at that. The last section, there's very little to actually explain other than the idea that like dissolves like. It is a very important concept, but as opposed to me trying to explain it via video, I think it makes more sense for you to go ahead and read it on your own. So please, after you have tried question 1, go on and read page 384 and 387, paying special attention to the content while keeping my line of like dissolves like in your head, okay? And try to explain this, explain what I mean by that, okay? If you have any other questions, please come and see me or send me an email, do whatever you need to. You are responsible for all this stuff, especially understanding, doing all the questions so that you are ready for the next video. The next 2 videos are going to go deeper into the idea of solutions. And it is very important that you understand how things dissolve and how things can remain as a solid, because they can't be surrounded by what they are not dissociated. Okay, and therefore they remain as a solid. Please go to your textbooks. When you're ready, let's take a look at the next videos. Okay, see you.